Well, I know you guys have missed me and my awesome videos, so let's get going with getting ready 4.1, and let's keep on things a little better for some of us maybe this term. Make sure we're paying attention. So, this one shouldn't be too bad. A lot of similar stuff that we've already been doing. So let's take a look at these first type of problems. Just basically recognizing those arithmetic and geometric sequences. So, to remind ourselves, arithmetic, they grow by addition or subtraction repeated. So, adding or subtracting the same number. And geometric, they grow by multiplication and division of that same number. Okay? And so neither would be everything else. It could be addition, subtraction, multiplication, division, but they're not going to be the same numbers. Okay? So now it wants us to justify. Justifying would be just probably showing what the pattern is. That would be a pretty good way to justify. Alright, so let's take a look at number 5. So we've got 40 to 10 to 5 halves to 5 eighths. Well, to get to 40 from 10 I can subtract 30, but if I subtract 30 again I'm definitely not getting to 5 halves, so I know it's not arithmetic. Okay? Pardon my computer, which was just starting. But so how do we get from 40 to 10? Well, that would be like dividing by 4. Well, what's 10 divided by 4? That would give us, if we reduced it, 5 over 2. Okay, so we're on to something here. Let's see if we do it again if we get 5 eighths. If we divide by 4, that's like 4 over 1. Remember, when you're dividing with fractions, you can't divide, you have to multiply by the reciprocal. So we get 5 over 8. So we're dividing by 4 each time, so this would be geometric. Another way to think about it is that I'm timesing by a 1/4. Same thing. Dividing by 4 and timesing by 1/4 are the same exact thing. Okay, now number 6. How do we get from 1 to 11? We're adding 10. 11 to 111, we're adding 100. Okay, so that's definitely not arithmetic. Can we multiply? 1 times 11 would give us 11. 11 times 11 is not 111, so it's not geometric either. Okay, so this pattern, there is a pattern, but it would be a neither, because we're adding by different numbers each time. That would be our justification there. Okay, now number 7, we've got negative 3.6, negative 5.4, negative 8.1. Well, how do we go from 3.6 to 5.4? Well, take the bigger one and subtract the smaller one and see what we get. 1.8. So if I subtract 1.8 from that, is that getting me 5.4? Yep. If I subtract 1.8 from that, are we getting negative 8.1? Well, negative 5.4 minus 1.8, okay, that's like plus a negative, so we could add them together. We get 2, 1, we get 6.2. Okay, so we're not doing that, so it's not arithmetic. So are we multiplying by a number? Well, grab a calculator and go 5.4 divided by 3.6, and let's see what we get. So when we divide those, we get 1.5. Okay, so it's like we are multiplying by 1.5. Well, let's try it again. Take that 5.4 and times it by 1.5, and we get 1.8 times 1.8 by 1.5. Do we get 12.15? And we do. So so it's geometric, and we are multiplying by 1.5. So when you're tested and you're not sure, it's not easy to see, just take the second number, subtract or divide by the first number, and then test that with the other ones. Okay? So number 8, we've got negative 64 to negative 47. So we could go 47 minus 64, or 64 minus 47. Okay, would be a good way to see that difference. So we'd borrow, we'd get 7, so we get 17. So are we adding 17 as we go from 64 to 47? Well, adding 17 again, 47 minus 17 would get us 30, and then adding 17 again would get us 13, so this one is arithmetic, and we are adding 17. So remember, that's how we figure out with the sequences what's going on there. Okay, now number 9 wants you to create a sequence that's not arithmetic or geometric. So basically, you've got to have some sort of pattern where the number is growing predictably. And a good one to think about is number 6. Okay, because I can tell you what we're going to add next, because we're adding a 0 each time we move on. So the next one would be 10,000. Okay, or some other good types are you start with a number and then you add 1, then you add 2, then you add 3, then you add 4, then you add 5, you know, something like that. So it'd look like this. Okay, so just make sure that it's something that's not predictable in the sense of the same number here, adding or multiplying, but that it is growing. Okay, and try to use one different than that. Don't just copy me. Use your imaginations. Come up with something cool. Okay. All right, now this one, discrete and continuous relationships. So the way to think about it is discrete just means that there's only certain places. There's not stuff in between. Continuous, there can be something in between. A good example here of continuous would be number 12. Because if I'm thinking about water flowing over the Niagara Falls, okay, so if I measured it in a whole day, they say it's 3.24 billion gallons. But what if I measure half a day? Can I measure half a day? Yeah, it still makes sense because that water's constantly flowing. I could measure per minute. I could measure per second. Okay, so basically, if you're thinking about the graph, okay, if we were to graph this and the time and the gallons, okay, yeah, one day it may be up here at 3.2 billion. And at, you know, the start of the day it would be at 0. But there's water flowing in between it. Okay, that's what makes it continuous. We can connect the dots because there's not something that stops us from doing that. A good example on this of discrete would be number 13. The average person laughs 15 times per day. Okay, well, when you're talking about laughs, can you have half a laugh? Some of you may say yes. You know, you start laughing when you're drinking milk and then you choke on it and then you almost die and everybody else is laughing at you. You might call that half a laugh, but we don't think of laughs in pieces. It's not like this water. You know, you either laugh or you don't laugh. And so I can laugh once, I can laugh twice, I can laugh 3 times, you know. And so there's not a way to connect the dots in between. If we graphed it, you know, it'd look something, you know, depending on how you graphed it, those dots wouldn't be able to be connected. That's what discrete means. There's not a way that we can connect them. Okay? So I want you to think about those other ones and try to figure out, you know, is it something that you can measure in between or not? Okay, can it not be measured in between? That's kind of the way you're thinking about these ones. So I want you guys to try the other ones, and then if we have more questions, we can talk about it in class. But that's the main gist of discrete and continuous. Continuous, you can measure in between the points. Okay, we can measure in between the days. The discrete, I can't measure in between. Okay, we can't have partial laughs. You either have a laugh or you don't. Alright? Let's take a look at these last types, the slopes of lines. Just finding slopes, a few different ways we can do this. If you look at 17, I've got 2 points here. Okay, what I can try to do is graph it. 0.5 is going to be a little bit tougher to graph though, but 0.5 and 4 would be right about there. 3 and 3.5 would be right about there. Well, this one's a bit tougher to graph, right? Because how far would we go down? Well, from 3 to 3.5, the y value, we'd go down a negative 0.5. How far over do we go? There's 1, there's 2, and then a half. So 2.5, so you'd go the y, negative 0.5 over 2.5, which then you'd want to reduce that and figure out what it is. We could divide both sides by 0.5. Or I guess a better way of thinking about that is, how can I make that a whole number? Well, 0.5, if we doubled it, we get 1, and if we doubled 2.5, we get 5. So that's one way that we can think about it. Probably an easier way on that one would be to do it this way. These are our y values, so it's the change in one y. What's the difference here? And then our x values, what's the difference here? And we get the same thing. We get 0.5 over negative 2.5, which then you can manipulate to get it going better. Okay? So it'd be negative 1/5. We don't like doing decimals. If you left it like this, that's alright, but we don't really like doing it that way. We prefer with slope to look like this. Okay, with whole numbers. And I guess if you're thinking graphically, if I went down another 0.5, that would get me to a whole number, and if I went over another 2.5, that would help with getting things to be a little bit more, being able to see. And then between these two, that's where your 1 and 5 come into play. Anyway, that's something we can do. Now for 20, what I can do is try to graph some of these. And once again, I've got a decimal, but I would just graph the numbers that aren't decimals, because we can always reduce. So I'd graph this and this. So negative 1 would be right there, and 1, 2 would be up there. Well, that's easy. 1, 2, 3 over 1, 2. So it'd be a positive 3 over 2. Okay, that's one way to think about it. Another way would be to just pick those 2 points and take the difference in the y's, negative 1 minus 2 over negative 1 minus 1, which would get us a negative 3 over a negative 2, which simplifies to 3 over 2. Okay, the other way would be kind of what we've been talking about with slopes, where we would say, how is the y growing? Well, we are adding 1.5, right, or 1.5 as we go this way. As we go this way, we're adding 1. So it's the y value over the x value. It'd be 1.5 over 1, which, how would we get this to be a whole number? Just double it, because it's a 0.5, so we'd have 3 over 2. Okay, so a lot of different ways you can attack that one, but use whichever way you prefer, and try your best at making sure they're not decimals, because we don't like, a decimal would work. We could still figure it out, the slope. We could still graph it, but we try not to.